there is a question that has a way of arriving uninvited. It tends to show up late at night when the house is quiet and the lights are off, and your mind, freed from the noise of the day, drifts toward the large things. It might come to you on a long drive, the road unwinding ahead in the dark, the radio turned down, the miles slipping past. It might arrive in the middle of an otherwise perfectly ordinary Tuesday afternoon, sandwiched between a sandwich and a meeting, landing without warning like a stone dropped into still water. The question is this: if the universe began, if the Big Bang was a real event, a moment at which space and time and matter and energy all came into existence from a state of extraordinary compression, then what was there before it? What existed in the moment before the moment everything began? What was the universe expanding into? What was happening in the time before time? And then, almost always, a follow-up question arrives hard on the heels of the first. Is that question even meaningful? Can there be a before if time itself began at the Big Bang? Can you meaningfully ask what came before the beginning any more than you can ask what is north of the North Pole? Most people, when this question arrives, do one of two things. They either file it under things too big to think about and return their attention to the sandwich, or they sit with it for a while, feeling simultaneously exhilarated and faintly dizzy, before eventually deciding that this is probably a question for physicists and philosophers and not for them. But here is the thing. The physicists and the philosophers have been sitting with this question for decades, and they have not filed it away. They have pushed into it hard with every tool available: mathematics, observation, theory, speculation, rigorously constrained by evidence. And what they have found is not a clean answer. It is something stranger and more interesting than that. What they have found is a collection of possibilities, each one stranger than the last, each one consistent in its own way with the physics we know, each one pointing toward a different picture of what, if anything, lay on the other side of the Big Bang, and each one raising new questions that are, if anything, harder than the one they started with. This is one of the deepest questions in all of science, and the answers, plural, contested, incomplete, brilliant, are worth knowing. Before we can talk about what came before the Big Bang, we need to be clear about what the Big Bang actually was. Because the popular image of it, a vast explosion, a fireball erupting outward into empty space, expanding in all directions from a single point, is wrong. Not slightly wrong or approximately wrong. Fundamentally, structurally wrong. And the misconception matters because it makes the question of what came before harder to think about clearly. The Big Bang was not an explosion in space. It was an expansion of space. The difference is enormous. An explosion in space has a center and an edge. It expands outward from one point into a pre-existing surrounding void. The debris flies apart through space that was already there. If you looked at the explosion from the outside, you could identify its origin and its periphery. The Big Bang had no center and no edge. There was no pre-existing void for it to expand into. Space itself, the very fabric of the universe, began expanding. Every point in space moved away from every other point. There was no outside. There was no vantage point from which to observe the whole thing happening. The Big Bang did not happen at a location in the universe. It happened everywhere, simultaneously. Every point you can identify in the observable universe today including the point where you are currently sitting, was, at the moment of the Big Bang, squashed into an unimaginably small, hot and dense state. And it is not just space that the Big Bang gave birth to, time too. This is the part that makes the question of what came before so genuinely hard. According to Einstein's general theory of relativity, the best description of gravity and space-time that we have, space and time are not separate things. They are woven together into a single four-dimensional fabric. And that fabric is dynamical. It can stretch and curve and warp. And when you run the equations of general relativity backward, tracing the history of the universe in reverse, watching the expansion reverse into contraction, the galaxies draw together, the temperature and density climb. You hit a moment, roughly 13.8 billion years ago, where the equations break down entirely. This moment is the Big Bang singularity. It is the point at which the density of the universe becomes infinite, the temperature becomes infinite, and the laws of physics as we understand them cease to apply. It is not simply the earliest moment we can currently calculate. It is, within the framework of general relativity, the beginning of time itself. Before the singularity, there is no before. Time did not exist. The question of what came before the Big Bang, within this framework, is like asking what lies south of the South Pole. It is not that the answer is difficult, it is that the question, as posed, has no meaning. Saint Augustine of Hippo, a philosopher and theologian working in the 4th and 5th centuries, 1,000 years before modern physics, arrived at essentially the same answer through pure reasoning. When asked what God was doing before the creation of the universe, he reportedly said that the question was meaningless because time was itself a part of creation. There was no before. There was nothing before. The universe, and time with it, simply began. It is a remarkable intellectual achievement, reaching the correct conclusion for the wrong reasons. But here is where things get interesting. General relativity, for all its extraordinary success, is not the final word on physics. It is a classical theory. It does not account for the quantum mechanical nature of matter and energy. And there is very good reason to believe that at the extreme conditions of the Big Bang singularity, quantum effects are not negligible. They are dominant. They are everything. A theory that ignores quantum mechanics is simply not adequate to describe the very earliest moments of the universe. And when you bring quantum mechanics into the picture, something remarkable happens. The singularity may not be real. The limits of the map. Think of general relativity as a map. It is an extraordinarily good map. It correctly predicts the bending of light around massive objects, the existence and properties of black holes, the expansion of the universe, the ripples in space-time produced by colliding neutron stars. It has been tested to extraordinary precision in every regime we can access experimentally, and it has passed every test without exception. But every map has edges. Every map represents a region beyond which the cartographer's knowledge ran out, and the parchment was left blank or decorated with sea monsters. General relativity's sea monsters live at the extreme limits of energy and density, at the centers of black holes and at the Big Bang singularity, where the curvature of space-time becomes infinite and the equations produce nonsensical results. Physicists call these regions singularities, and the consensus view is that singularities are not real features of the universe. They are features of the map. They are places where the theory is telling you, in the most emphatic way possible, that it has reached the boundary of its own applicability. They are the equation's way of waving a flag and saying, something else is going on here, something I cannot describe. You need a better theory, the better theory, the one that would correctly describe physics at the densities and temperatures of the very early universe, would need to be a theory of quantum gravity, a framework that combines the insights of general relativity with the principles of quantum mechanics. Such a theory does not yet fully exist. The search for it is one of the central projects of theoretical physics. String theory and loop quantum gravity are the leading candidates, as we have explored elsewhere, but neither has yet delivered a complete, tested, predictive account of quantum gravitational physics. However, even without a complete theory of quantum gravity, physicists have been able to make progress on the question of the early universe by taking the tools we do have: quantum mechanics, general relativity, quantum field theory, and pushing them as far as they will go. And what emerges from this effort is not one answer to the question of what came before the Big Bang, but several. Each one the product of a different theoretical framework, a different set of assumptions about what the correct theory of quantum gravity will look like. Each one compelling, each one incomplete. Let us take them in turn. The no-boundary proposal. In 1983, Stephen Hawking and the American physicist James Hartle published a paper that proposed a radical answer to the question of what came before the Big Bang. Their answer was that the question has no answer, not because it is meaningless, as Augustine suggested, but because of a specific and precise mathematical reason. Their proposal is called the no-boundary wave function, or sometimes the Hartley-Hawking state. It draws on a mathematical technique borrowed from quantum mechanics called a path integral, a way of calculating the probability of a physical system moving from one state to another by summing over all possible paths between them, each weighted by its quantum mechanical probability. To apply this to the universe as a whole, to ask, what is the quantum mechanical probability for the universe to be in its current state? Hawking and Hartle proposed imagining the history of the universe not in ordinary time, but in what mathematicians call imaginary time. Imaginary time is not a science fiction concept or a metaphor. It is a specific mathematical operation, replacing the time coordinate with a quantity involving the square root of -1. This sounds arcane, but it has a profound effect on the geometry of space-time. In ordinary time, the Big Bang singularity is a sharp point, a boundary, an edge, a place where the universe begins and beyond which there is nothing. But in imaginary time, Hawking and Hartley showed the singularity disappears. The geometry smooths out. Instead of a sharp point, the beginning of the universe becomes rounded, like the South Pole of a sphere. The South Pole is a well-defined point on the sphere, but it is not a boundary. There is no edge to fall off. You can move away from the South Pole in any direction and simply find yourself moving along the surface of the sphere. In the Hartle-Hawking picture, the beginning of the universe is like that. There is no boundary, no edge, no moment before which there was something else. The universe simply is, complete in itself, with no prior cause and no exterior. Time, near what we call the Big Bang, loses its character as a time dimension and becomes, in effect, a spatial dimension. There is no before, because the geometry has no beginning, only a rounded, finite, boundaryless surface from which time, as we experience it, emerges. This is a beautiful idea. It is mathematically elegant, conceptually radical, and it genuinely dissolves the question of what came before the Big Bang, rather than merely pushing it back a step. But it raises questions of its own. Imaginary time is a mathematical tool, the physical interpretation of what it means for time to be imaginary near the Big Bang. What it would actually feel like, or look like, or mean to exist in a region where the time dimension is behaving like a spatial one, is not entirely clear. Hawking himself sometimes spoke of imaginary time as if it were the more fundamental reality, with ordinary time an emergent approximation that arises at later epochs. But this interpretation is not universally accepted, and there is a deeper issue. The no-boundary proposal does make predictions about the universe, specifically about what kind of universe it is most likely to produce. The universe it predicts most probably is not, by some calculations, the large, smooth, flat universe we actually inhabit. This tension between the predictions of the no-boundary wave function and the observed properties of our universe is a subject of ongoing research and debate. The no-boundary proposal may be correct. It may be approximately correct. It may be pointing in the right direction without quite hitting the target. We do not know. Inflation and its discontents. To understand the other leading proposals for what came before, or instead of, the Big Bang singularity, we need to introduce a concept that has become central to modern cosmology: inflation. In 1980, the American physicist Alan Guth proposed that the very early universe went through a period of extraordinarily rapid expansion, an expansion so fast that it dwarfs anything that has happened in cosmic history since. During inflation, the universe doubled in size not once or twice, but perhaps 60 or 70 or 100 times in the space of a tiny fraction of a second, something like 10 to the minus 32 seconds. The universe grew from something smaller than a proton to something roughly the size of a grapefruit in essentially no time at all. Inflation was proposed to solve several puzzles about the observed properties of the universe. Why is the cosmic microwave background, the afterglow of the Big Bang, the oldest light we can see, so extraordinarily uniform across the entire sky? Regions of the universe that are so far apart, they could never have been in contact, even if signals had been traveling between them at the speed of light since the beginning of time, nonetheless have temperatures that agree to better than 1 part in 10,000. In the standard Big Bang picture without inflation, this is deeply mysterious. Inflation solves it. All the regions we can observe today were once in close contact before the inflationary expansion stretched them to cosmic distances. Why is the universe so geometrically flat? So close to the critical density that divides a universe that will eventually recollapse from one that expands forever. Inflation solves this too. Rapid exponential expansion flattens out any initial curvature, just as inflating a balloon makes its surface look flatter and flatter. And why are there no magnetic monopoles? Exotic particles predicted by grand unified theories that should have been produced copiously in the hot early universe, but which have never been observed. Inflation dilutes them to undetectable levels, stretching the universe so rapidly that the density of any pre-existing exotic relics drops to essentially nothing. Inflation, in short, explains the large-scale properties of the universe with remarkable success, and it makes testable predictions, particularly about the statistical properties of the tiny fluctuations in the cosmic microwave background, which inflation produces from quantum fluctuations and then amplifies to cosmic scales. Those predictions have been confirmed with extraordinary precision by satellite observations of the microwave background. Inflation is not fringe physics. It is close to mainstream cosmology's best current understanding of the universe's first moments. But inflation has a consequence that is deeply relevant to the question of what came before the Big Bang. Inflation almost certainly did not last forever in the past. The theorem that establishes this is called the Border-Guth-Vilenkin theorem, after the three physicists who proved it in 2003. Arvind Borde, Alan Guth, and Alexander Vilenkin. It shows that any universe in which the average expansion rate has been positive over its history must have had a beginning. It cannot have been expanding, even inflationally, exponentially, forever into the past. There must have been a moment before which the inflationary expansion did not exist. Inflation does not get rid of the beginning. It pushes the beginning back and packages it differently, but the beginning is still there. The question of what came before it, what started inflation, and what existed before inflation started, remains unanswered. And it is here that the most exotic proposals enter the picture. The eternal bouncing universe. One of the oldest intuitions about the universe is that it has always existed, not in the specific form it takes now, not with these galaxies, these stars, these planets, but in some form. The universe, on this view, has no absolute beginning and no absolute end. It cycles, it bounces, it contracts and expands, dies and is reborn over and over again, in an eternal rhythm that has no first beat and will have no last. This idea, called the cyclic or oscillating universe, has roots in ancient philosophy and has been periodically revived by physicists over the decades. The modern version, developed in the early 2000s by Paul Steinhardt of Princeton and Neil Turok of the Perimeter Institute, is called the ekpyrotic model, from the Greek word for conflagration. The ekpyrotic model is rooted in string theory. It proposes that our universe exists on a three-dimensional surface, a brain in the language of string theory, embedded in a higher dimensional space. Another brain exists nearby, separated from ours by a small distance in the extra dimension. Ordinarily, the two brains are parallel and do not interact, but they are attracted to each other by a force. Not gravity exactly, but an effect of the higher dimensional geometry. And periodically they come together and collide. When the brains collide, the energy of the collision is deposited on our brain as a hot, dense, nearly uniform plasma. In other words, it looks, from the perspective of beings living on the brain, exactly like the Big Bang. The laws of physics fill space with radiation and matter. The brain begins to expand and cool. Galaxies form, stars ignite, life, perhaps, emerges. And then, over an extraordinarily long period, trillions of years, the expansion slows, the matter and energy thin out, and slowly, almost imperceptibly, the two brains are drawn together again. Another collision is coming, another Big Bang. In this picture, the Big Bang was not the absolute beginning of everything. It was a collision between two pre-existing surfaces in a higher dimensional space. Before the Big Bang, on the other side of the collision, there was a previous cycle of cosmic history, just as rich and complex as ours, and before that, another. And another. The universe has no beginning and no end. It simply cycles. The ekpyrotic model is scientifically serious. It makes specific predictions about the properties of gravitational waves in the early universe that differ from the predictions of inflationary models, and future observations may eventually be able to distinguish between the two. But it faces difficulties of its own. The physics of brane collisions is not fully understood. The transition from contraction to expansion, the bounce, involves extreme conditions where the equations become unreliable, and the model requires the machinery of string theory, which itself remains unconfirmed. But as a proposal for what came before the Big Bang, it has a powerful virtue. It is concrete. It gives the question a concrete answer. Before the Big Bang, there was a previous universe, a previous cycle, a previous age of cosmic history, separated from our own by the collision that gave our universe its birth. The quantum creation of everything. In 1982, a young Russian-American physicist named Alexander Vilenkin proposed something that sounds, at first hearing, completely outrageous. He proposed that the universe tunneled into existence from nothing. Not from a previous universe, not from a higher dimensional space, not from some pre-existing substrate of any kind, from genuine, absolute nothing. Vilenkin's proposal draws on a phenomenon in quantum mechanics called quantum tunneling. In classical physics, if a particle is sitting in a potential well, trapped in a valley with hills on either side, it can only escape if it has enough energy to climb over one of the hills. It cannot pass through the hill. The barrier is impenetrable. Quantum mechanics says otherwise. Because of the wave-like nature of quantum particles, there is a finite probability of finding a particle on the other side of a barrier, even if it has insufficient energy to cross it classically. The particle, in a sense, tunnels through the barrier rather than going over it. This is not a hypothetical or an approximation. It is a real and experimentally verified phenomenon. It is the principle behind nuclear fusion in the Sun. Without quantum tunneling, protons could not fuse at the temperatures in the solar core. And it is the basis of the scanning tunneling microscope. Vilenkin proposed that the same principle applies to the universe as a whole. The universe, he argued, could have quantum tunneled into existence from a state of literally nothing. No space, no time, no matter, no energy, no physical laws. Nothing whatsoever. The probability of such tunneling is not zero. It is extremely small, but in quantum mechanics, extremely small is not the same as impossible. The universe simply appeared, not from a prior cause, not from a pre-existing physical state, from nothing, through the mechanism of quantum tunneling. Before the universe, there was no before. There was no time in which nothing existed waiting to become something. The universe, with its time and its space and its matter and its energy, tunneled into existence as a complete quantum event. Vilenkin's model produces a universe that begins in a tiny, compact state and then inflates. It predicts that the universe should be geometrically flat and nearly uniform, in good agreement with observation. And it answers the question of what came before with an answer that is philosophically uncomfortable but physically precise. Nothing, not the nothing of empty space. Empty space is something, a quantum vacuum seething with virtual particles and fields. True nothing, the absence of everything, including space and time themselves. Whether this is satisfying is a matter of taste. Some physicists find it deeply compelling. The universe came from nothing because given enough quantum mechanical probability, something rather than nothing is almost inevitable. Others find it philosophically troubling. The quantum tunneling process itself requires quantum mechanical laws to operate, and those laws seem to be something rather than nothing. Where did the laws come from? Did they pre-exist the universe? Do the laws of physics exist independently of any physical reality? These questions do not have agreed answers. The conformal cyclic cosmos, Roger Penrose, is one of the most distinguished mathematical physicists alive. He shared the 2020 Nobel Prize in Physics for his work on singularity theorems and general relativity. Proofs that, under very general conditions, singularities like the Big Bang are mathematically inevitable in Einstein's theory. He has spent a career doing things that other physicists initially thought were impossible. In the early 2000s, Penrose proposed a model of the universe's history that is, in its way, among the strangest ideas in modern cosmology. He calls it conformal cyclic cosmology, or CCC. The model begins with an observation about the very far future of the universe. The kind of cold, dark, empty future we explored in the context of the last star. As the universe ages and expands, as black holes evaporate and matter decays, and the cosmos approaches thermal equilibrium, something interesting happens to the mathematics describing the universe's geometry. At extremely late times, in an essentially empty universe dominated by radiation and the cosmological constant, the universe's geometry becomes what mathematicians call conformally equivalent to the geometry of the Big Bang. Conformal equivalence is a precise mathematical relationship between two geometries that preserves angles but not scales. A conformal transformation can stretch and squeeze a geometry without limit, as long as it does so consistently. Two geometries that are conformally equivalent can look very different in their scales, but are identical in their angular relationships. Penrose's insight was that the remote future of one cosmic cycle and the Big Bang of the next are conformally equivalent. They can be mathematically glued together. The end of one universe, in the appropriate mathematical description, is identical to the beginning of the next. There is no singularity at the transition. The geometry is smooth. Time flows continuously from one eon to the next. In CCC, our universe is one eon in an infinite sequence of eons, each one beginning with what looks like a Big Bang and ending in the cold, dark, conformally equivalent geometry that seamlessly transitions into the next eon's beginning. There is no absolute beginning and no absolute end. The question of what came before the Big Bang has a specific answer: a previous eon, a previous universe. Not separated from ours by a high-energy collision or a quantum tunneling event, but connected to ours by a smooth mathematical continuation that makes the boundary between them a matter of description rather than a physical barrier. Penrose has made a striking observational claim that signals from the previous eon, specifically the gravitational waves produced by the mergers of supermassive black holes in the previous eon, should leave detectable imprints on the cosmic microwave background of our own eon. These imprints would appear as concentric rings of slightly anomalous temperature, centered on the positions in the sky where the previous eon's black hole mergers occurred. There have been claims, contested, of finding such rings in the microwave background data. The mainstream view is that the evidence is not compelling, that the claimed signals are consistent with statistical noise. Penrose disagrees. The debate continues. CCC is not widely accepted, but it is taken seriously by some very serious people. And it represents one of the most creative and mathematically sophisticated attempts to answer the question of what came before. The multiverse and eternal inflation. There is one more major proposal to consider, and it is perhaps the most expansive of all. It grows from the same inflationary cosmology we discussed earlier, and from a property of the inflationary process that its original proponents did not fully anticipate. The universe, according to inflationary cosmology, underwent a period of exponential expansion driven by a field, the inflaton field, that temporarily held the universe in an energetically false state. As long as the inflaton field remained in this false state, the universe inflated. When the field decayed to its true ground state, inflation ended, and the energy of the field was converted into the hot, dense plasma, particles and radiation that we call the Big Bang. This is the standard picture of inflation. But in 1986, the Russian-American physicist Andrei Linde noticed something about this picture that changes everything. The inflaton field, like all quantum fields, fluctuates. In most regions of the inflating universe, the field decays and inflation ends. But in some regions, those in which quantum fluctuations happen to kick the field to a higher value rather than a lower one, inflation does not end. It continues. It accelerates. The inflating region grows faster than the regions where inflation has ended. And within that still inflating region, further quantum fluctuations occasionally kick the field even higher, creating sub-regions where inflation accelerates further still. The result is that inflation, once started, never fully stops. In any given region, inflation will eventually end and a Big Bang will occur. But new inflating regions are constantly being created by quantum fluctuations. The volume of inflating space grows without limit. Inflation is eternal. Not in the past, which the Border-Guth-Vilenkin theorem prevents, but in the future. And each region where inflation ends is a separate universe. A pocket universe, a bubble universe, an island of ordinary physics embedded in an ever-expanding sea of inflating space-time. Our universe is one such bubble. It formed when inflation ended in our particular region, roughly 13.8 billion years ago, and surrounding it at distances so vast they are beyond any conceivable observation are other bubble universes, other Big Bangs, other cosmic histories, other sets of physical laws. This is the multiverse, not a philosophical speculation, but a prediction. Some physicists would say an unavoidable consequence of the most widely accepted model of the universe's early history. If eternal inflation is correct, then the question of what came before the Big Bang has an extraordinary answer. Before our Big Bang, inflation was happening. And before that inflation was happening in our region, other bubble universes were forming in other regions, and before those, more inflation, more bubbles, an endless proliferating foam of universes without limit. The Big Bang was not the beginning of everything. It was the beginning of our particular island of organized physics in a vast, eternal, ever-expanding sea of inflationary space-time. The multiverse raises as many questions as it answers. If there are infinitely many universes with different physical laws, why do we find ourselves in one with laws hospitable to life? The answer that most inflationary multiverse proponents give involves the anthropic principle. We find ourselves in a life-permitting universe, because only in life-permitting universes can anyone ask the question. But whether this constitutes a scientific explanation or merely a restatement of the obvious is a matter of genuine disagreement among physicists and philosophers. And the multiverse itself is, almost by definition, unobservable. Other bubble universes are separated from ours by a barrier of inflating space-time that nothing can cross. Their existence makes our universe possible, but it cannot be directly confirmed. Whether a theory that makes predictions only about unobservable entities qualifies as science in the full sense is a question that strikes at the foundations of what science is. These are not comfortable questions, but they are the right questions. Loop quantum cosmology and the quantum bounce. Among the candidates for a theory of quantum gravity, loop quantum gravity has produced one of the most specific and dramatic proposals for what happened at and before the Big Bang. Loop quantum gravity, as we explored earlier, proposes that space itself is quantized, that at the Planck scale, below around 10 to the minus 35 meters, space is not a smooth continuum, but a discrete network of finite quanta. Space is not infinitely divisible. There is a smallest possible chunk. When physicists apply this framework to the cosmology of the early universe, a field called loop quantum cosmology, something remarkable happens to the Big Bang singularity. It disappears. In classical general relativity, running the universe backward in time leads inevitably to the singularity, the point of infinite density and infinite curvature where the theory breaks down. But in loop quantum cosmology, the discrete nature of space prevents the geometry from reaching zero volume. As the universe contracts, as you run time backward toward the Big Bang, the density and curvature increase. But before they reach infinity, the quantum repulsive effects of the discrete space-time structure kick in and reverse the contraction. The universe bounces. Instead of collapsing to a singularity and ceasing to exist, the universe contracts to a minimum volume, enormously small but finite and well-defined, and then rebounds into expansion. The Big Bang is not the beginning of everything. It is a bounce. On the other side of the bounce was a previous phase of the universe, a contracting phase, a universe that was once large and expanding, that contracted and compressed to the minimum volume, and then bounced back into the expanding universe we now inhabit. Before the Big Bang, in this picture, there was a universe, a different universe, one in which the arrow of time pointed in the opposite direction from ours, in which the universe was not expanding but contracting, in which the stars and galaxies of a previous cosmic age were being drawn toward each other by a reversed expansion that ended in the maximum compression from which our universe was born. Loop quantum cosmology makes specific predictions about the imprint of the pre-bounce universe on our own. The quantum fluctuations from the pre-bounce phase should affect the properties of the cosmic microwave background in detectable ways. Observations by future experiments, particularly measurements of the polarization of the microwave background, which encode information about the very earliest moments of cosmic history, may eventually be able to test these predictions. The quantum bounce is not a confirmed picture of the universe's history, but it is a mathematically precise, physically motivated proposal that dissolves the singularity and replaces it with a smooth transition between a pre-existing universe and our own. All of these proposals, the no-boundary wave function, the ekpyrotic bouncing brains, quantum tunneling from nothing, the conformal cyclic cosmos, eternal inflation, the loop quantum bounce, share a common challenge. They all, in different ways, have to confront the problem of time. Time is both the subject of the question, what came before, and the most conceptually slippery ingredient in any answer. We experience time so directly, so immediately, so inescapably that we tend to assume we know what it is. But we don't. Not really. Physics has deepened the mystery rather than resolving it. In Newtonian mechanics, time was absolute. It ticked away at a fixed rate everywhere in the universe, indifferent to what was happening within it. Einstein destroyed this picture. In general relativity, time is elastic. It stretches near massive objects and at high speeds. It is woven into the fabric of space-time, and it can, in principle, be curved or warped by extreme matter distributions. And in quantum mechanics, time has a strange status. It is not, in the standard formulation of quantum mechanics, and observable in the way that position and momentum are. It is a parameter, something that equations depend on, something that progress is measured in, but not something that quantum systems have a definite value of in the way they have definite values of other quantities when measured. This makes combining quantum mechanics with general relativity, in which time is a dynamical part of the physical system, deeply problematic. In the Wheeler-DeWitt equation, an early attempt to write down the quantum mechanics of the universe as a whole, derived by John Wheeler and Bryce DeWitt in the 1960s, time disappears entirely. The equation describes the quantum state of the universe, but it has no time variable. It is a timeless equation. The universe, at the deepest quantum mechanical level, may not change in time. Time may be emergent, a concept that arises at some level of approximation when you look at the universe in a certain way, but that has no fundamental status in the ultimate description. If time is emergent, if it arises from something deeper and more fundamental that is itself timeless, then the question of what came before the Big Bang may not ultimately be a question about time at all. It may be a question about the structure of the timeless quantum state from which time emerges, and about what features of that state give rise to the appearance of a beginning. This is not a solved problem. It is barely a well-posed problem, but it is the direction in which the deepest thinking about the Big Bang is currently pointed. What the observations tell us. In the midst of all this theory, it is worth pausing to consider what observational evidence we actually have about the earliest moments of the universe, and how far that evidence reaches toward answering the question of what came before. The furthest back we can see with light is the surface of last scattering. The moment, roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into hydrogen atoms, and the cosmos became transparent. Before this moment, the universe was an opaque plasma, and light could not travel freely. We see this moment in the cosmic microwave background, the extraordinarily uniform glow of radiation that fills the sky in every direction, the fossil light of a universe that was once unimaginably hot and dense. The properties of the microwave background, its uniformity, its tiny temperature fluctuations, the statistical patterns of those fluctuations, encode information about what the universe was like in its first moments. They confirm the broad outlines of the inflationary picture. They are consistent with inflation having occurred. They do not yet tell us which version of inflation, or whether what came before was a bounce or a tunneling event or a previous eon. To reach further back, to probe the universe in the first fractions of a second after the Big Bang, or to find evidence of what came before, we need different messengers. Gravitational waves can travel through the opaque plasma of the early universe and reach us from moments that light cannot. The primordial gravitational wave background, if it can be detected, would carry information from the inflationary epoch itself, and might encode signatures of the pre-bounce or the pre-tunneling state. Experiments are underway to find this signal. The BICEP and Keck Array experiments at the South Pole and their planned successors are searching for the characteristic imprint of primordial gravitational waves in the polarization of the cosmic microwave background. So far, no confirmed detection has been made, but the search is narrowing the range of possibilities and ruling out classes of inflationary models. We are not yet able to observe before the Big Bang. But we are developing instruments sensitive enough to observe the Big Bang itself in ways that carry information about what preceded it. The answer to the question, or a constraint on the answers, may be observable within the coming decades. What we do not know, it is time, as in every honest account of a frontier science, to take stock of what we genuinely do not know. We do not know whether the Big Bang singularity is real or an artifact of the breakdown of general relativity. The singularity is a prediction of classical general relativity. All of our best evidence suggests that classical general relativity is not a complete description of physics at the smallest scales and highest densities. Whether the singularity is replaced by a bounce, a tunneling event, a smooth, no-boundary geometry, or something else entirely, depends on the correct theory of quantum gravity, which we do not yet have. We do not know whether time had a beginning. The question sounds metaphysical, but it is physically precise. If the no-boundary proposal is correct, time did not begin. It smoothly transitioned from a spatial dimension into a time dimension as the universe emerged from the Planck epoch. If loop quantum cosmology is correct, time extended through the bounce from a previous cosmic phase. If quantum tunneling from nothing is correct, time came into existence as part of the tunneling event, from a state in which time had no meaning. We do not know which of these is correct, or whether any of them is. We do not know whether the multiverse exists. Eternal inflation predicts it. It is unobservable in principle, not merely in practice. Whether a theory that predicts unobservable entities is scientific in the full sense, whether it can, in any meaningful way, be tested and falsified, is a question on which physicists and philosophers of science are deeply and genuinely divided. We do not know whether the laws of physics are fixed or variable. If the multiverse is real and different bubble universes have different physical laws, then the laws governing our universe are not universal truths but local accidents. The strength of gravity, the mass of the electron, the energy of the vacuum, all of these could have been different in a different bubble. The universe we inhabit is the way it is not because the laws of physics demand it, but because we happen to be here. This is either a profound insight or a troubling abandonment of the explanatory ambitions of physics. Probably it is both. And we do not know, at the deepest level, why there is something rather than nothing. All of the proposals we have examined, the bounce, the tunneling, the eternal inflation, the conformal cycle, assume some prior structure, either a pre-existing inflating space-time or the laws of quantum mechanics themselves, or the mathematical framework of conformal geometry. None of them begins from truly nothing, in the sense of the complete absence of any mathematical or physical structure whatsoever. The question of why there are laws at all, why mathematics exists, why anything should be rather than nothing. This question lies, at present, beyond the reach of physics. It may always lie beyond the reach of physics. It may not. Science has a long history of answering questions that previously seemed permanently unanswerable. The edge of the map. Go back to the late night, the quiet house. The question arriving uninvited. You know more now than you did. You know that the question is not meaningless. Or rather, you know that whether it is meaningful depends on which theory of quantum gravity turns out to be correct, and we do not yet know that. You know that the singularity at the Big Bang may not be real, that it may be the edge of the map rather than the edge of the territory. You know that some of the most creative and rigorous minds in physics have proposed specific, mathematically precise answers to what came before. A previous eon, a previous contracting universe, a quantum tunneling from nothing, an eternal sea of inflating space-time from which our Big Bang was one bubble among uncountably many. You know that none of these answers is confirmed. You know that the question pushes us to the absolute frontier of what physics can currently say, and then a little beyond it, into territory that may require a theory we do not yet have. And perhaps most importantly, you know that the question is not one that human curiosity invented to torture itself. It is a question that the universe has, in a sense, posed to itself, because the only way we know anything about the Big Bang, the only way we know that 13.8 billion years ago the universe was hot and small and expanding, is because the universe produced through a long and improbable chain of stellar explosions and planetary chemistry and biological evolution and cultural development, creatures capable of wondering about such things. The universe is, to the best of our knowledge, the only thing in existence that can ask questions about its own origin, and it is asking, loudly, persistently, with every particle accelerator and microwave telescope and gravitational wave detector we can build. The question of what came before the Big Bang is not a question at the periphery of science. It is not a question for idle speculation or late-night philosophy. It is the question that every theory of the fundamental nature of reality must eventually answer. It is the question at the heart of cosmology, at the intersection of the largest and smallest scales in physics, at the place where general relativity and quantum mechanics must finally be reconciled. We do not have the answer yet, but we know, far more precisely than any previous generation of human beings, what the shape of the answer must be. We know what it must dissolve, the singularity, and what it must preserve. The laws of quantum mechanics, the geometry of general relativity, the observed properties of the microwave background. We know which observations could distinguish between the competing proposals, and we are building the instruments to make those observations. The edge of the map is not the edge of the world. Beyond it, there is territory. Strange, counterintuitive, mathematically demanding, philosophically vertiginous territory, but territory nonetheless. And we are walking toward it, one equation at a time. You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.